Okay. Thank you, Dimitri, for the invitation and for the very kind introduction. It's a pleasure to be here. And today I'll tell you about heavy quark transverse momentum dependent fragmentation. This is my work in collaboration with Rebecca, who is a PhD student at Daisy, and Johannes, who is a postdoc at ECAF. And don't worry about the title if you don't understand some part of it. I'll explain it all very soon. Okay, so most of my work is on QCD, quantum kernel dynamics, and this is the part of the standard model that describes the dynamics of quarks and gluons, which make up hadrons at this confinement scale, which I'll take to be around 200 MeV. And hadrons are what makes up the matter around us. We think about hadrons using our brain, which are made of hadrons, and we study them at colliders, the Large Hadron Collider in particular, but also other colliders such as E+C- colliders at Bell and so on. And I'll discuss phenomenology towards the end of the talk as well. There are many theoretical challenges in QCD. So first of all, nonperturbative calculations is very hard. So we try our best to calculate perturbatively, but still it's hard to quantify nonperturbative effects. There's also this phenomenon called confinement. We don't know the exact dynamics of how confinement happens, but this also means we cannot observe quarks and gluons directly, which makes study of the theory harder. We are interested in the internal structure of hadrons and the dynamics of hadronization, like how confinement happens physically. But because these are real-time dynamics, we cannot easily simulate them on the lattice, which is the best tool that we have to study QCD. So these are also interesting challenges. People are interested in precision measurement of the strong coupling constant to reduce theoretical errors from the standard model, and this is an active field of research. We're also interested in exotic forms of matter, such as quark-gluon plasma and neutron stars. And these are all scopes of QCD, and these are all active fields of research. And today, I'm just going to focus on these two items, which is the internal structure of hadrons and the dynamics of hadronization. And I'm going to study it using fragmentation functions of heavy quarks. So here's a quick outline of what I'm going to talk about today. I'm going to introduce all the elements in my title, heavy quarks, fragmentation, and transverse momentum distributions. Then we'll put things together and consider heavy quark TMD fragmentation. And this is an interesting effective field theory problem because you have different parametric regimes, which I'll discuss in detail later. And because of heavy quarks effective theory, you also have spin symmetry relations that can have phenomenological implications. And then at the end, I'll discuss phenomenology at colliders, existing B factories or the future EIC. And then I'll give you a brief summary. Okay, so here's my title, heavy quark, transverse momentum dependent fragmentation. We'll start with heavy quarks, by which I mean the bottom and charm quarks. So they are special because they have mass m much larger than the confinement scale lambda QCD, but they're still smaller than the hard scale of the problem, the hard scale of the collision. And because they have mass much larger than lambda QCD, we can use heavy quark effective theory, HQET, and the expansion parameter is naturally lambda QCD over MQ. And in this effective theory, we have heavy quark spin and flavor symmetry. So the flavor symmetry is basically if you have a heavy quark and a heavy Q and a heavy quark Q prime, they are not the same flavor. The effect from this difference of flavor is 1 over MQ suppressed. And same for the spin symmetry, which is if you have spin up and spin down, at hadron level, this effect is also 1 over MQ suppressed. But we can do expansion order by order in the theory, of course, and you can calculate these effects. But today, all of the talk will be at leading order of 1 over MQ. And heavy quarks are ideal probe of hadronization because they act like a static color source. So in this naive drawing, so if you have a light quark, the hadronization process is basically magic because everything is at order lambda QCD. The heavy quark is the mass is the light quark mass is below lambda QCD, and the gluons dynamics are around lambda QCD, and you basically just have everything. You don't know how the dynamics are happening. But heavy quarks are different because the mass is so much heavier than the confinement scale. It propagates through the dynamics of hadronization and form a heavy hadron H at the end. And this process is basically transparent compared to the dynamics of hadronization. And I have a cute analogy. So this is, anyone take a guess of what this picture is?
No. What's it?
Any takers?
A look testing the pool.
No. Why did I show all this? Okay.
Smoke?
Okay. What if I do this?
It's current.
It's like a wire going through.
That's right. It's a wire, a copper wire going through iron films. So the copper wire.
This doesn't comply lab safety standards because it's not insulated as well.
Oh no. Good thing that we're theoretical physicists, so we don't care about safety.
But you're in the national lab, you have to be careful.
Okay.
It's virtual, so.
Yeah, but so the copper wire carry a current that's going through this iron filing, and the point of the analogy is that the current going through the wire is a static electric source, and this is making the dynamics of electromagnetic force transparent when you have a static source. And you can think of heavy quarks as a static color source, and it will make the dynamics of hadronization more transparent. So this is why we want to think about heavy quarks as a probe for hadronization processes.
Question. So
yes.
For that one, you cannot have only one quark follow.
Yeah, of course not.
So
No.
you
This is
combine together several heavy quarks, or a heavy quark together with a light quark or something.
I mean, if you think about collider processes, you produce them by pair production, and they go back to back.
Okay.
So for one side, you basically just
Oh, okay.
Go.
So I can reverse this process.
yeah, of course. And heavy quarks also have a rich phenomenology. So beyond QCD, people care about flavor violation, extraction of CKM matrix elements, and CP violation, and so on. And there are existing experiments such as Bell, Babar, and LCB, who all study like B quarks in particular. And so there's a rich amount of data for us to analyze in this field of study. So that's the motivation for why we care about heavy quarks. Why do we care about fragmentation? So fragmentation is an intrinsically non-perturbative process. It basically describes the hadronization process, and the dynamics, as I said before, is of order lambda QCD. And fragmentation basically describes how a parton, meaning a quark or gluon, become a hadron. And this process is described by what is called the fragmentation function, D, of hadron H out of Q. So what is this fragmentation function? A fragmentation function D of H out of Q, H being the hadron, Q being a quark, depends on the longitudinal momentum fraction that the final state hadron carries with respect to the initial quark. And this basically describes what's the number density, in a sense, that you would find a hadron carrying momentum fraction Z that's initiated by a quark Q traveling this longitudinal direction with momentum P. And these fragmentation functions show up in collider process cross sections. And this is a statement of factorization, which is you can factorize the hard part of the collider process out and then describe the nonperturbative part by these fragmentation functions. So consider E plus E minus 2 dihadron. You have quark antiquark pair going out, and one quark becomes hadron H1, and the antiquark becomes hadron H2. And then for this process, the cross section is proportional to the convolution of these two fragmentation functions, H1 out of Q and H2 out of Q bar. And other processes that fragmentation functions come in are semi-inclusive deep inelastic scattering. And for this case, you have a electron colliding with a proton, and for semi-inclusive DIS, you measure one outgoing hadron, and this outgoing hadron comes from a quark that hadronizes into this hadron H. So for this process, you have this D fragmentation function. But this process also depends on what is called the parton distribution function, which describes how a quark is coming out of this initial state proton. This parton distribution function, PDF, also depends on the longitudinal momentum fraction. In this case, we usually call it X. X is the quark longitudinal momentum fraction inside of a hadron, as illustrated by this naive picture here. So semi-inclusive DIS is a fragmentation function with a PDF. So why do I care about these functions? It's important to note that they're universal nonperturbative functions, meaning that once you specify the quark and the hadron, they're universal across processes. So this function really is determined by the quark and the hadron, and you imagine it as a distribution of the momentum fraction. And because they show up in many different cross-sections, you can imagine like extracting this function from one type of experiment and use it as input for another type of experiments. And for E to dihadron processes, the experiments that are active are Bell and Lab. And for semi-inclusive DIS, you have Jefferson Lab and the future EIC doing these type of collisions. So now the final missing piece of the title is the transverse momentum dependent part. So what do I mean? This is actually very self-explanatory. It just depends also on the transverse momentum, KT. So transverse being relative to the longitudinal direction that we were considering before. So these are the canonical PDF and FFs. So they depend on the longitudinal momentum. But now we consider the transverse momentum as well. So this FF and PDF gets upgraded in a sense to the TMD FF and the TMD PDF. And now they not only depends on the longitudinal momentum fraction, but also on the transverse momentum.
The transverse momentum is, according to your cartoon,
yeah,
you're talking about the transverse momentum of the
quark, yeah.
Of the quark respect to the hadron. Instead, normally it's the other way around. You have some kind of for fragmentation function. You initially have a hadron and have a quark.
Yeah.
And then there is transverse momentum between the quark and the same thing between the hadron and the initial quark.
Right. The thing is, you always have the freedom to choose frame. And because of momentum conservation, you can always choose a frame where the quark carries the leading transverse momentum. So you can think about it this way also.
So why should the fragmentation? I see that I need information about the transverse dependence of the PDF, right? This extra information is nucleon. But now I have this struck quark. Why would this care about the transverse the fragmentation depend on the transverse momentum of the struck quark? Whether the quark flies this way or this way, should they fragment the same way?
Well, as I just explained, it really depends on what frame you're thinking about this in, right? But the easiest frame to think about this is maybe think about EE collision, and then you have back-to-back production of quark antiquark pair. And if you radiate off a gluon, it gives the quark a non-trivial transverse momentum, right?
Yeah, but if I know the quark fragmentation function, I just make a rotation into the direction of the quark and be done with it. So I don't see why I should my fragment, I have a quark flying through space.
Yeah.
And the fragmentation function tells me what comes out of this quark. Whether the quark flies in this direction, or this direction should be
Yeah, but the thing is, that is really just the parton level picture, right?
Yes.
But in QCD, the quark is flying around with a bunch of gluon with it, so whether you made a gluon really is encoded in transverse momentum part of this distribution, right? This is like radiation off the axis.
That's my understanding. Normally, that's my normal understanding is that you have the quark going this direction, and then find that the hadron come out with sort of transverse momentum with respect to the quark. That's my understanding. Original transverse momentum dependent
that
quark
also,
fragmentation function, right?
But that I can understand.
Yeah. So it does not really matter whether the quark go in any direction. It's only the relative transverse
The angle between the hadron and the quark.
Yeah.
Oh, okay.
Yeah.
That I think.
Okay, good. All right, well, and then here is, so when you consider transverse momentum, you have what's called the TMD factorization framework, which is really a well-established theory framework of how you can factorize these cross-sections at colliders in terms of these TMD-dependent distribution functions. So the requirement for TMD factorization is the transverse momentum should be small compared to the Hart scale. And this would be a natural power counting parameter that you use for writing down the transverse momentum dependent cross-section for these processes. By transverse momentum dependent, I just mean your cross-section is differential with respect to KT. Okay, so now if we want to write down like rigorous equations, we can of course write down the field theoretic definition of the TMDFF correlator, and this is written in position space. So what you have here is, so you have a quark field, two quark fields, and they are addressed with Wilson lines, and the Wilson line is also in position space. And then you have this sum over state X, which is basically all the, so you specify the hadron that the quark is fragmenting into, and the X is everything else in this process, and you are summing over X. And the trace there is a trace in color space. And this position space variable B perp is the Fourier conjugate of the transverse momentum. And my light cone conventions, if anyone cares, is like this. So we are explicitly choosing a frame that the hadron transverse momentum is 0, so the transverse momentum in a sense is carried by the quark, which is clarified.
A question.
Yeah.
So here the transverse actually is referred to the hadron, so you cannot isolate. You always have a reference, which is a hadron. You cannot isolate the quark talking about transverse, right?
Yeah.
Okay.
Yeah.
So, but if the hadrons are in different directions, then every time do I need to define the transverse direction?
So in collider processes, you define it with respect to the beam axis or the back-to-back axis. So you have choices, but you can relate them.
Okay.
So for the purpose of this talk, I'm going to define the sum also over hadron helicity. This is not necessarily a choice you have to make, but I'm considering basically experimentally unpolarized final state hadrons, and then you have this sum over hadron helicity at the end.
So your line, W is the line operator?
W is the Wilson line.
So that's making cage invariant,
Yeah.
right? But it's passive. I mean, you could choose different paths corresponding. So how do you think about that?
So W, I just write down, like, when you think about collider process, you factor it in, like, in SCHQET, for example, and you choose a light cone momentum. You choose the light cone direction, and then you write your Wilson line in that, in terms of that light cone direction.
Yeah, I understand what you do, but.
Yeah.
Okay.
And these two are separated in position space as well.
So narrowly, because it's all final state, so there's only one direction.
There's only one direction?
Yeah. For power distribution, you do have choice of bipolar or forward. And then for the fragmentation bond is always forward.
It's always forward. Okay.
Yeah, okay. As I said, well, you didn't have to sum over the final hadron spin, and if you don't, if you resolve the polarization of the final state hadron at leading twist, you would have 8 fragmentation functions, TMD fragmentation functions. But because I am summing over the hadron polarization, we're restricted to the unpolarized final state hadrons, in which case you only have 2 TMD fragmentation functions to worry about. One is called the unpolarized TMDFF, and the other one is called the Collins TMDFF. So they're defined in terms of the TMDFF correlator that I showed you before through a Dirac trace with some projectors inserted. So these are the 2 non-vanishing Dirac structures you can consider for unpolarized final state hadron. And these are just their definitions that you can write down. And in the rest of the talk, I will continuously refer back to these objects. But yeah, basically the unpolarized is unpolarized. You have an unpolarized quark and an unpolarized hadron, whereas the Collins describes the quantum correlation of the quark transverse polarization with the final state hadron transverse momentum. But I'll make that more clear later. So now, if we put everything together, this has actually never been studied before until we put out this study last year around this time. And we can consider heavy-quark TMD fragmentation functions. So what is this all about?
So you said that you studied before is the light quark?
Yeah, so light quark TMD. Yeah, this is light quark. This is all in the light quark, or like you're agnostic about your quark. So you just write down a generic quark field, but you don't consider, okay, what simplification can we have in the case of a heavy quark? And that's like what we do here. We consider specifically in the framework of HQET, how can you simplify this picture?
In the light quark, if you don't know how to compute, but in the heavy quark, she will show how to compute.
Yeah, there are more computations you can do, and you have.
mean sort of like coordinate effective theory?
Yeah, because the TMDs are easy to compute.
I guess you can probably study the evolution problem.
Oh, that's you can, but they, I mean, sure, maybe talk about how they compute this actually in the effect theory.
Yeah, you can see what we can compute in this framework. So the framework is HQET, where you can. Let me first discuss the tools of HQET that we will use for the rest of the talk. So the first one is tree level matching from QCD to HQET, where you have the field, quark field matching like this, and the outstate, external state matching like that. And this V mu is the direction of the heavy quark, and you have reparametrization variance. So it doesn't matter which direction V you choose, but for us, we'll choose it to be in the direction of the hadron momentum. And then another very useful tool from HQET is you can do what is called the stereo decoupling, which allow you to further write this heavy quark field H of V in terms of a static color Wilson line Y of V and a free Dirac field HV of 0. So this free Dirac field has nice property where when it acts on the final state, it really just gives you a Dirac spinner. And once you have Dirac spinners, you can imagine like later when you sum over states, you can get completion relationships, and this is what simplifies our calculation later. Yeah, so here the light degrees of freedom is encoded in the final state, of course, but also in the static color Wilson line, which has soft gluons attached to it. But the heavy quark has become a free direct field by itself, and this is what simplifies the computation later.
So in this case, you basically assume all this soft radiation does not affect the spin structure of the heavy quark.
Yeah. So as I mentioned before, so because of we're now in the regime where you have heavy quark mass and also lambda QCD and the hard scale, this is a multi-scale problem, and you can consider two different parametric regimes of where the transverse momentum is in terms of this hierarchy. So on the left, you can have transverse momentum set by the soft radiation. And in this case, the nonperturbative matrix element will have KT dependence. And on the right, the transverse momentum is set by the scale of perturbative emissions. And in this case, the KT dependence would all be in the perturbative matching coefficient. So the computation actually plays out quite differently. But we're going to, but it's important to remember that KT should always be parametrically small than the hard scale so that you can still work in the regime of TMD factorization. Okay, so let's start with regime 1. Regime 1 is where KT is set by the soft radiation. And this is more interesting because your nonperturbative matrix element has the KT dependence. So what we do in this regime is we match the correlator in QCD onto HQET by performing the tree level matching. And this allows you to write the TMD correlator, TMD-FF correlator in terms of a HQET matrix element, which I will call f of h. And this has all the transverse momentum dependence because this is the non-perturbative part, and the non-perturbative dynamics has the KT dependence. And you have this delta function up front, which is really telling you that the heavy hadron should retain most of the transverse moment, retain most of the collinear momentum from the quark. And this is at leading order of 1/mq, of course. And at higher orders in 1/mq, you would have non-distributional dependence on ZH.
Question.
Yes.
So TMD-FF is what you have introduced, which doesn't specify the mass of the quark.
Yeah.
HQET is a specific case you're applying.
Right. So this is in HQET, and this is in QCD.
Okay.
Yeah. Very good. So now we have made the transition by doing the tree level matching from QCD to HQET. Okay, and then we can evaluate the unpolarized and colons TMD-FF in HQET using the HQET matrix element. And just a reminder that their QCD definition is like this, and you basically just substitute this correlator with the matched onto HQET correlator that you have just computed, and you would have these two, what we call the heavy quark fragmentation factors, and they're defined in terms of this f of h, this HQET matrix element. Just to illustrate, so in QCD, you have the full dependence, the full D1 and H1 perp in terms of the QCD correlator, and after you do matching onto HQET, all the non-trivial dependence are on these two heavy quark fragmentation factors, and you have, of course, the matching coefficient from before. And using previous tool, we can actually have a all-order perturbation theory, all-order in alpha S result by using this CM perturbative matching coefficient, which bridges QCD and HQET through SCET. So now with the delta function up front, you actually have, you can actually write the full TMD fragmentation functions in terms of these two HQET matrix elements, all ordering in alpha S.
What's the M here?
M? Which M?
The order and all of M.
Mass of the heavy quark.
Okay, what for C-quark, not so large, I mean, not so small.
I mean, depends on what parametric regime you choose lambda QCD, right? If lambda QCD is 100 MeV, then the mass of charm is big. But yeah, of course, this approximation that leading order is better for bottom for that reason. But since you're operating in an EFT regime, you can always compute to higher orders. It's like allow you to quantify your error, right? This is why we're effective field theorists. So what we can do in HQET is we can consider the heavy-quark spin symmetry. So we analyze this HQET matrix element f of h, and we use the HQET tool number 2, heavy-quark stereo decoupling. This would allow us to separate the light degree of freedom, the light dynamics, all into this light spin density matrix. So how does this work? So recall that stereo decoupling separates the color and spin, and the heavy quark now become a free Dirac field. And when you act it on the final state, it gives you just Dirac spinners. And these Dirac spinners are here. And since we're summing over a lot of the quantum numbers, they basically give you a complete relationship of in terms of Dirac space. And then the rest of the light dynamics is written in terms of Clebsch-Gordon coefficients, determined by the spin and helicity of the heavy quark, which we know is just 1/2 plus minus 1/2. Spin of the light degree of freedom, so depending on which light quark you're hadronizing into your final state hadron, and then the final state hadron's quantum numbers. So become more clear now. So let's consider the unpolarized TMDFF first. For the unpolarized TMDFF, we can write it in terms of the Dirac trace of the HQET matrix element like so. And then because it's unpolarized, it's actually diagonal, so you get a squared of the Clebsch-Gordon coefficients. Again, depending on the quantum number of the heavy quark, the light degrees of freedom, and the final state hadron. And what you can do to make this more transparent, let's consider the light degree of freedom being just another light quark. So SL will be 1/2. And then the final state hadrons would you can have SH equals 0, which gives you a D meson in terms of a charm quark and a light quark. And you can have SH equals 1, which gives you a D star meson, so the excited state with a charm quark and another light quark. And what the analysis gives you is just because of the proportionality of the Clebsch-Gordon coefficients, you actually have a direct proportionality of the transverse momentum fragmentation functions. So D of the unpolarized TMDFF of D meson is 1/3 that of the D star meson, just because the D star meson have 3 spin multiplets. This is because they're governed by the same light dynamics, because you have chosen SL equals 1/2. And so this part just factors out, and the proportionality comes from the Clebsch-Gordon coefficients. And this is a testable result of heavy quark spin symmetry. You can test this at colliders, which I'll talk about more in the final part. Yeah.
So here, does this test include both your assumption that they can be separated plus times the heavy quark spin symmetry? Because the expression here is based on the assumption that you can factor out the color and spin.
Mm-hmm.
So testable result should be a combination of that assumption and this spin symmetry, right?
I mean, that assumption is true in HQET.
Okay, yeah.
Yeah.
So
it's true at order 1/m, like at leading order of 1/m.
So, but actually you should test both. Well, for the assumption should be true, but the test for that include both.
Are you saying that like if you include higher order mass effect, that would be violated?
No. I'm saying like this test means your assumption is true and having quark spin symmetry is okay. Not just this one. I think it should include the testing of that assumption. That
I mean, but the assumption is like really not an assumption in HQET. It's really just a.
yeah, the assumption of HQET should also work to get this result.
Like assuming HQET work, you would get this?
Yeah.
I mean, sure, because we're in the framework of HQET, right?
Yes, but to test it, you should also test HQET as well. Not assuming, but it's
Okay, thanks for the comment. And then another interesting thing that show up from this analysis is if you actually sum over all the final state hadrons of, say, a charm quark could form, then you have a complete sum over state, and you can actually complete the sum over X that I wrote down in my correlator, and you would get a vacuum matrix element of just purely Wilson lines. And this thing you can try to compute on the lattice. And we're actually currently working with people at MIT, the lattice group, trying to say what we can compute, like how much we can compute of this object. And this would actually be the simplest observable that you can get out of this, basically. And now let's move on to the Collins TMDFF, which is really just a different projector of the same matrix element. And as I mentioned before, the Collins function, which might not be as familiar, is a quantum correlation between the initial quark's transverse spin and the transverse momentum of the final state hadron. And you might naively expect, because it depends on the initial quark's transverse spin, since we're in HQET, maybe this is 1/m suppressed, right? But this is actually not true, and you can get an intuitive sense by looking at this drawing. So for the light quark case, of course, the transverse momentum, the hadron transverse momentum and the light quark transverse spin is just governed by QCD Lagrangian, and this correlation is fully encoded in the QCD Lagrangian, so no surprise there. But for the in the heavy quark case, the QCD Lagrangian, or rather the light degree of freedom, correlates the light quark initial spin. So the you can think of it as the spin of the light degree of freedom, but in case of a meson, it's just a light quark. This part of the correlation is governed by the light Lagrangian, but an experimental measurement of distinguishing the D meson versus the D star meson, for example, correlates the light quark spin and the heavy quark spin. And this correlation does not care about mass whatsoever because it's just a measurement. And combining these two correlations, we actually are just left with the Collins function, which is the correlation between the final state transverse momentum and the initial state heavy quark transverse spin. So this is actually not suppressed by heavy quark mass, which is interesting because Bell and Babar and their experimental papers usually consider the heavy quark Collins effect as a background towards the light quark one. And this analysis is saying you should instead measure the heavy quark Collins effect instead of considering it as background because it's not suppressed. The same heavy quark spin symmetry analysis give us interesting sum rules in case of the Collins function. So again, taking my archetypical example of D versus D star meson, it's actually saying the Collins function, when you sum that of the D and the D star meson out of a C quark, you get 0. So they're exactly opposite of each other. And this is another testable result of the heavy quark spin symmetry. Okay, so this is regime 1. Let me just give you a quick summary. So what we did is to match the TMDFF correlator in QCD onto HQET. And then this allows us to write the full TMDFF in terms of the matrix element in HQET. And the transverse momentum dependence is really all in these HQET matrix elements. But we analyzed the spin symmetry and found interesting proportionality in some rules, and these can of course be generalized to higher light degree spin. But I was just using D versus D star meson as an example.
Well, if this can the measure, this D and D star, this with Collins function.
Mm-hmm.
So then if the sum is 0, then the sign is opposite. Is that
Yes.
the prediction?
Yes. The thing is, you don't measure one of these at a time. You always measure it with a PDF or with another FF. Without telling more about
you can measure D and D star separately.
Yeah. But I'll tell you about that in the phenol section.
Before we go on, so can you have a model calculation? I mean, I know, for example, you talk about that maybe in the future we can do an lattice calculation to get some handle of this. I'm just curious about the Collins effect again. I mean, now I understand because normally in the night sector, the Collins function naively just equals 0 because that involves helicity flipping. So you do need a non-perturbative mechanism to generate non-zero Collins from the function. Yeah. Or otherwise you have to need a Hartree effect from the function to get a non-zero Collins from the function. But in the heavy sector, the helicity flip would depend on quark mass.
Mm-hmm.
I mean, that's basically because they have mass, so the helicity can be flipped when you do the calculation. Yeah. So in a sense, the helicity flip will proportional quark mass. So I'm wondering if there's any model calculation to actually show that.
There's any model calculation?
Yeah. I have no idea. I mean, I never done any calculation in the HQET. HQET is the effective theory, right? So, but I think maybe at the very early beginning, people also have some model calculation for that, right? You just assume some wave function for the heavy mesons, then you can do a computation.
Yeah, I'm also not familiar with this part of the literature.
Otherwise, this is still like a black box, right? You don't know anything, right? Although you say this is not surprised by heavy-quark mass, but yeah.
Well, okay, in this regime,
still, F itself is like a black box.
Yeah, in this regime, the transverse momentum is still like in the matrix element, but in the next regime, you can actually do the calculation. Yes. So this is where I'm going next.
Oh, okay.
In this regime,
okay, then you answer my question.
In this regime, KT is set by the perturbative the emissions, and so it's on the order of like mass of the heavy quark or above. And then in this case, you can all the transverse momentum dependence is actually in the perturbative matching coefficient. So for the unpolarized, it's quite simple. We just call this matching coefficient D1QQ, and then there's only one HQET non-perturbative matrix element that you can match this onto, and this actually has been studied before. This is called the total probability of the quark to fragment into the hadron H, and this has been studied like since the 70s, since the 90s, and this really is the previous like matrix element evaluated at BT equals 0. Yeah, and this has been like studied even in the heavy quark regime. But what we did later is we can calculate this perturbative matching coefficient because now it's fully partonic. You do it by Feynman diagrams, and we actually recently did this to Neptune leading order in alpha S. And the result is out as of April, and it's the real emission are these two diagrams. And I'll just talk about this very briefly because I don't have much time left. But there's actually a very interesting renormalization structure of this calculation where you have to use 2D plus distributions to normalize all the poles at like Z goes to 1 and KT goes to 0. But after doing this analog calculation, we're actually enabling the next to leading log resummation for the heavy hadron like TMDs. And there's a direct application to capture the mass effect of a back-to-back energy correlator as well. So this is a useful calculation to have, not just for theory purposes.
But when you do the French transfer, you have to go to KT about the non-QCD region, right? So how you deal with that? So you just keep the KT much larger than non-QCD in this calculation.
Oh, I mean, like, I see what you mean. The KT much larger than lambda QCD. I mean,
That's
larger
right,
than lambda QCD is not a problem.
Yeah, that's right.
Yeah.
But when you try to match to the phenomenology, you do have to do the fully transform, right?
Yeah.
Then KT has to go to
I
small.
mean, small.
Yeah.
Yeah, but this, I mean, you can always argue this for whatever Fourier transform you do wherever, right?
Okay.
And people still trust Fourier transform.
Okay. Got you.
That question has been asked since my first ever QCD. My first ever QCD project is this transverse momentum integral of the TMD-PDF, right?
That's right.
Anyway, now we can move on to the Collins fragmentation function. And what we do here is, so there's existing result from the light quark twist expansion, and you probably know this equation quite well. This matching has been done for the light quark case, and we just simply generalize it to a heavy quark, and you again only have one nonperturbative HQET matrix element that you can match onto. And then the result is quite, again, like straightforward. You have this delta function like before, and it's linear in BT, and then you have this matrix element from HQET. And heavy quark spin symmetry play out exactly the same in this regime as before. Now your like matrix element does not depend on transverse momentum anymore. But these relationships are like point by point true in the transverse momentum space. So like every point in the transverse momentum, you can test these relations. And that's important. And I should have said that in the last regime as well. But yeah, these symmetry relations are true throughout, like no matter where your transverse momentum is. And so here we come to a summary of the regime 2. Again, we did perturbative matching. So now all the all the KT dependence is in the perturbative matching coefficient. And specifically for the unpolarized TMDFF case, we can calculate the partonic matching coefficient D1QQ, and we have done it to NLO by now. And we recover again the heavy quark spin symmetry relations of these sum rules and proportionality relations. And so now I can talk about phenomenology. So let's start with a reminder of how we factorize collider processes into these fragmentation functions that I've been talking about. So at E plus E minus collider, you have EE collision to dihadrons. And in that case, you have two fragmentation functions. So two TMD fragmentation functions, as I talked about, the subject of this talk. And then in EP colliders, you have one fragmentation function with a PDF, TMD PDF. And we actually also calculated all the TMD PDF as well, and you can find the result in the paper, but I don't have enough time to go over them, but you can ask me about them later. So at EE colliders, the interesting phenomenology is to consider the Collins effect. So where does the Collins effect come from? So when you measure the differential cross section in PT, you can factorize this cross section into different structure functions. So this unpolarized part is two unpolarized FF together, and this Collins part is two Collins function together. And there's other structure functions, but they're not for unpolarized final state hadrons, so I'm not going to discuss them here. And the Collins effect is the proportionality of the two Collins function part of the structure function over the unpolarized part of the structure function. And this has a cosine 2 phi.
0 is the angle between
the angle of the hadron.
Between two hadrons or between one hadron?
The
one
azimuthal hadron of the hadron that you measure with respect to the beam.
Okay, it's just one single. Okay.
Yeah,
You're
it's
looking
just
at
one.
just single hadron.
Yeah. So this Collins effect has a cosine 250 modulation, and this is how you can like extract this part because you can track this modulation basically. And we have did some like very crude like numerical like calculation, and these are percent effects at existing B factories. And you can definitely measure and extract this effect. Percent level should be doable with current like data analysis techniques. And the thing about measuring the Collins effect is that because there are two Collins functions, you cannot extract the sign, and the sign is of theoretical interest because it relates to the Wilson line direction that you asked about earlier for the transverse function. We can, so this part is for the Collins effect, but I also told you earlier that the results from heavy-quark spin symmetry should be testable. So how exactly it works out is if you measure the Collins effect for a D bar, it should have this set of proportionality versus if you measure like a D star D bar or a D bar star or a D star bar. These factors of 1/3 is because of all the heavy-quark spin symmetry relations that I derived earlier. And this proportionality can be tested at existing B factories for sure. And for EP colliders, we have a similar factorization theorem, and it's written in terms of one fragmentation function and one PDF. And the PDF part we calculated as well, like in the paper, but I'm not going to show them here again. But for the interesting part of the EP collider, which we can definitely resolve with the future EIC, is now that you have one single Collins function showing up in this factorization theorem, since we have calculated this TMD PDF part, you can now extract this one single Collins function, and then you can get its sign. And the sign is, again, a percent level effect at, say, even like Jefferson lab type of experiments, or EIC for sure in the future. And then you can extract the sign of the Collins function, which will be very interesting. And now I'm going to give a quick summary, and then we can answer any questions.
This is DIS, right?
Yeah, this is semi-inclusive DIS. Yeah, EP version. Okay, so I motivated heavy quarks as probes for hadronization, and in our work we studied the heavy quark TMD fragmentation functions for the first time. And in this study we find that this is a very interesting EFT problem. You have two parametric regimes. We defined some novel HQET matrix elements that's corresponding to the unpolarized and the Collins TMD FFs. And we also calculated a new perturbative matching coefficients to next to leading order. We have some testable results for heavy quark spin symmetry, and this allows us to talk about the exciting phenomenology at existing B factories and also the future EIC. And this is all. Thank you. Any questions? Yes.
Well, just to like, this is maybe still like very, I don't know what we can do that experiment, but suppose you do neutrino scattering, and there the heavy quark is not coming from pair production of blue anymore, but rather is through the charge current, and that probably have a sort of very different behavior because the normal QC process you have the pair production produce Q bar, but there essentially you convert a light quark into a heavy quark.
Yeah.
Maybe there's something interesting to look at.
I mean, sure, the electroweak part is you converted light quark into a heavy quark.
Yeah.
But because these are, nonperturbative universal functions, once you specify the final hadron and the heavy quark, it's still the same TMD fragmentation function.
At least maybe the perturbative part will be different.
Yeah, the perturbative part will surely be different in some region.
Part maybe the same,
So, when you make prediction, what assumption you have for these cosine 2 phi Collins effects? So it depends on this chi, right? Depends on chi1, that's an unpolarized case.
Oh, you mean like for the plot that I made?
Yeah.
What assumptions? Oh, yeah. So the models we used are very simple. We just like give it a Gaussian distribution with some nonperturbative parameters, and these nonperturbative parameters are all ordered on the QCD.
Okay.
Which is like generically how you would expect these things to be. And
But you mentioned that, for example, the chi there, that's really it's been calculated in HQET.
chi h, you mean?
Chi1 or whatever. For the
Yeah.
unpolarized case, that
Yeah,
matrix has been computed, right?
And I wouldn't say computed, you can say extracted.
Oh, extracted.
Yeah.
Okay.
Yeah.
Because of BDK. From the BDK.
I'm not sure what they extracted from, but the like total fragmentation probability is probably like you can.
So, but
extract
for the Collins one, you just made a parametric.
Yeah, we
whatever.
just make a parametric like
estimate.
no, yeah, like I mean for this just crude like estimate of how much percentage effect you have on experiments, right? But yeah. But everything like of this model, it should be like ordered on the QCD, and then we do the like of course perturbative evolution up to the scale.
So to model you again, so you mentioned this sum rule which give you matrix in between vacuum. Can you do the same for the Collins one? Maybe not. Maybe Collins one. So for the unpolarized case, you sum all the hadrons, all the Harry flavors. That it can be.
The one to the vacuum matrix on the
Yes,
lines.
which can be computed on that.
I don't
Do you
think
have
you can because Collins effect really like
Of course, there's a cancellation. There's a cancellation between different Harry mesons. But maybe there's a residual.
I don't think you can because the because what worked for the unpolarized is because if you think about like spin space, that matrix is diagonal. But for Collins, it's off diagonal.
Off diagonal, that's right.
And I don't think you can complete the sum in that case anymore. And you wouldn't have this nice like complete relationship of like x sum over it is 1, which is what's important for that vacuum matrix element.
Yeah, that could be.
Can you go to the slide with the expectation value you said you might be able to get from the HQET?
I can.
Just run.
Yeah.
So, and then W and Y are
2 different types of Wilson lines. So Y is the HQET Wilson line, it's off diagonal, it's off the light cone on lattice, and W is on the light cone. So you have to do some sort of limit for that part. Yeah. But Josh is working on that.
okay.